Hello. Yeah, I said that Dorothea couldn't get my name wrong when she introduced me. So I'm going to talk about surface mass balance. Okay. So hopefully, I mean, obviously for this audience, we don't need to explain the importance. But when we're talking about Antarctica, it's important that we understand not only the mass losses that are through the melt and some of these dynamic processes, but it's also really important that we understand the surface mass balance, what's actually going into Antarctica, the mass gains. And the best way of us understanding that in the past, over the longer time period, is looking at the snow accumulation from ice cores. So for the sake of this talk, when I'm talking about surface mass balance and snow accumulation, I mean the same thing. So the main reason why, as well, the surface mass balance, and particularly in going into the future, is so important is because it has the potential to mitigate or offset some of the losses that we're seeing from melt. And so back in the work that we did through these compilations of all the different ice cores around the continent, we were able to show that actually during the 20th century there has already been this mitigating effect. So largely the sort of regional differences in the snow accumulation can be attributed to changes in circulation, but the underlying sort of increase that we're seeing during the 20th century is related to changes in temperature. So this is based on the physics, the Clausius-Clapeyron relationship, that essentially means a warmer atmosphere is a wetter atmosphere. And interestingly, I guess for us and for the policy, is that under future warming scenarios, then there's this prediction that actually the snowfall is going to continue to rise. And there have been publications based on modeling studies that actually suggest that this may be enough to offset entirely the mass losses from Antarctica. However, this is also in sort of competition to this idea that actually it's not just, the snow falling on Antarctica, but where it falls is really important. So we've got these sort of thermodynamic processes potentially increasing the snowfall, locking it away. But then we have this dynamic effect, because where the snow is actually falling can act to accelerate the flow around the edges of Antarctica, which will actually, again, sort of, contribute to the sea level. So for the purpose of my study, I'm sort of going back from doing these more continental reconstructions and just focusing on the smaller regional sections. And what I want to do is just update some of the reconstructions of surface mass balance, just focusing on the Antarctic Peninsula, because this is the area that we've really seen the most significant increases in snowfall during the 20th century, and really focus on where is it actually, where is the snow falling. So this is the picture from our 2019 paper showing these big contrasts, and Quentin's just done a great explanation of the Amundsen Sea low to explain why we've got these sort of contrasting changes of big increases in snowfall on the Antarctic Peninsula, but then these sort of less increase in snowfall, the red areas here, so we've got mass losses around the Ross Sea. But importantly, the amount in gigatons, is pretty huge. So in Peninsula, it's increasing at a rate of 9.5 gigatons per decade. So updating, just to introduce you to some of the new records in here. So the work that we did previously was just based on 7 ice cores, and we've actually increased now the spatial coverage to try and really separate between these high and low elevation sites. So this includes a number of new records, and I just want to quickly introduce a little one from a subantarctic island, because I think it's important when we're talking about the ice sheet that we're really, these dynamic changes are happening around the edges, and we do have the opportunity to actually get to these edges, these low elevation sites, and the subantarctic. So this is a little tiny 12-meter fern core from Peter First Island. So it's the first ice core that I know of that's been drilled there. And even though it's only a very short record, so it's only covering from 2001, so it kind of makes it difficult to really sort of draw too many conclusions about this, what we are able to do is compare it with the reanalysis data to sort of get some confidence in the fact that actually extracting snow accumulation records from these very small islands not only tells you something about what's happening at that particular site, but it tells you about what's happening across the entire region. So the spatial correlation plot here is just showing you that actually snow accumulation in this very sort of targeted site can tell you a lot about what's happening across the Bellingshausen Sea. So that's just one kind of new addition that we've got to this. So we've also been adding to it by looking at low elevation sites. So we particularly want to get below that 1,000-meter mark, which is actually a little bit trickier logistically. But we've got a couple of new sites that are below 1,500 meters. And then also we've got some new sites from high elevations. So it's important, I'm trying to really capture as much of the sort of range of elevation changes across the peninsula. And one of the things that we have been doing is actually going back through our archive. And so this is a core called AP88, drilled in 1988, very close to the location of the Dyer Plateau ice core. And actually, it's been sat in our freezer for a very long time, and we went back and reanalyzed it, because it's actually, again, able to demonstrate just how important these changes in elevation really are. So there's quite a big offset between two sites that are only 6 kilometers apart and 50 meters of elevation. So, you know, in terms of the information we're putting into our models for future changes based on surface mass balance, you know, where these surface mass balance records are coming from is really important. So what we've been doing with this, and this is sort of more for kind of leading into the future work, is just really confirming that there's difference in elevation. So we do see a very clear linear relationship when we start looking at the snowfall on the high elevation sites versus the snowfall in the lower elevation sites. And this is going to be really important for how we calibrate our records later on. And I'm just showing you here all the dots I should have mentioned before, all the little dots. The colours correspond to the annual precipitation from the ERA 5 reanalysis. So just to confirm that we're, the reanalysis data set, the ERA 5 at the moment, is really good at capturing all these sort of smaller scale changes, which is reflected in the different snow accumulations at the ice core sites. However, there is a slight underestimate, so this may be to do with the resolution of the model, but as we saw in the difference between those two sites of just 6 kilometers apart, these changes can be huge over very small spatial scales. So jumping to try and get onto some of these reconstructions then. So the first plot that I'm showing you here is the reconstruction, and this is a composite, so I'm combining all of the different records that we have. And the top were the ones that we published in 2017 and 2019, and then at the bottom just updating that by including these new records. And what we can actually find is, so, you know, the first obvious thing is that we're able to extend a bit further back with these new records, so particularly the Palmer ice core and the sites from Dyer extending this record further back in time. And although they're both still, we're obviously still capturing this very big increase during the 20th century, when we actually put this into numbers, we can update this slightly. So our original estimates of 144 gigaton change during the 20th century was actually potentially a little bit of an underestimate. And this is because we're inputting that new data, particularly from that low elevation, those low elevation sites. And so this is just really showing, you know, there's pretty big numbers here. We're talking about 221 gigaton difference between the sort of 1600s and the last decade of the record. Now what I want to do is separate this, you know, rather than just looking at its composites per region, separating this out into elevation. So on the top, I'm showing the high elevation sites. So these are all the ones above 1,500 and the sites from below 1,500 at the bottom. And the reason, you know, this is actually showing, we're still showing the same kind of trends, so they're both showing that there's been this increase, but the amount of snowfall in both sites is quite different. So what we're seeing happening at the low elevation sites, not unsurprisingly to us, is nearly double what we're seeing at these higher elevation, colder sites. And so I'm just going to try and separate this out, you know, try and make it a bit simple what I'm talking about. So the high elevation sites highlighted around here in this sort of orange, these are sites along the ice divide, so it's somewhere where we assume is relatively stable, but in terms of when we start to put this onto a temperature as well, these are the cold, stable areas of the Antarctic Peninsula. Temperatures really drop, you know, annual average temperatures just shown here from ERA 5 in the order of about -25. So this is, you know, if we go back to putting this, this sort of schematic up here of where the snow is falling, snow falling in these high elevation sites presumably are going to be acting to mitigate the sea level because they're relatively stable, we're not expecting any melt, and so, yeah, this is kind of a good place for the snow to be landing. However, it's quite a different story when we then talk about the snow that's falling below 1,500 meters. So just highlighting around here in the red, this is the really dynamic region. And so when we add more snowfall onto this particular region, we then trigger this sort of dynamic acceleration of the melting and sort of increasing the flow. And just showing on the map here, you know, just taking some of the examples that we already know this is a really dynamic area, that we have seen these big changes across, across the grounding lines, it's across the ice shelves, and we know that these changes have been taking place in recent decades. And in some places, you know, there's numerous different studies, but just sort of different examples showing that there's been an acceleration in the order of about 50% on the sort of velocities in this region. So I guess my thinking or question is, you know, can some of this already be explained by these big increases in snowfall? I'm going to just really touch on this quite quickly, just sort of some of the drivers. So it's important for us, and actually Constance has done a great sort of introduction, so this is for me, but it's important that we understand what's driving this, and are the processes going to be different at the low and the high elevation sites? Because in terms of our future predictions, you know, this is going to be really key for us. So just separating again, trying to stick with the orange and the reds to separate the high and the low elevation sites. What it seems to suggest is that actually things like the southern annular mode, so changes in the westerly winds and the atmospheric circulations, this seems to have a much stronger influence on what's happening at the lower elevation sites. But interestingly, it's the Amundsen Sea low seems to have a stronger influence on the higher elevation sites. And in terms of the temperature, again, maybe not surprisingly, but these low elevation sites are a lot more sensitive to changes in temperature. So I guess my sort of final thing is, thinking of how this can link into the models and predictions for the future. These low elevation sites are a lot more sensitive to changes in the circulation and changes in temperature. And so I think perhaps, a lot more work could be done on really understanding this thermodynamic and dynamic influence of changes in surface mass balance. And with that, I'll finish.
Thank you very much, Liz. Any questions? One in the middle there.
Where? Sorry.
Just there.
Thank you, Liz, for the talk. So I was wondering, you said that there is more precipitation and larger increase at high elevation, but if you look in percentage, are they more similar, the percentage increase, instead of absolute numbers?
So there's more at the lower elevation sites.
Yes,
they seem to be increasing. The sort of trend seems to be going the same, and it's just the the actual kind of amount.
But if you look at the percentage, is the same percentage increase, or is still very different? So it's one is increasing more in percentage than the other region?
Yeah, in percentage, the lower elevations are increasing more.
Okay.
So, yeah.
Both in absolute and in relative value, then.
Yeah.
Okay, thank you.
Thank you.
Okay, our next speaker is Yusuke Suganuma, who is talking about East Antarctica and CDW-caused ice shelf collapse.